The inner solar system is defined by extreme environments, but the most hostile is found closest to the Sun. Looking at this stark dividing line, you can see the result of a planet without a true atmosphere to insulate it. On the day side, temperatures reach 800 degrees Fahrenheit, while the night side drops to -290 degrees. From the surface, the Sun appears more than 3 times larger than it does from Earth, bathing the landscape in intense solar radiation and plasma activity. Traveling at nearly 29 miles per second, Mercury whips around the Sun in just 88 days, locked in a tight, highly eccentric orbit. These environmental extremes are the direct result of Mercury's proximity to the Sun, but that same proximity provides the raw materials and energy density that could support a permanent human presence. Mercury is the second densest planet in the solar system. A massive iron core makes up over 40% of its volume, generating a surface gravity of 3.7 meters per second squared. This matches Mars almost exactly, providing a stable baseline to prevent human muscle and bone atrophy. This infographic maps Mercury's surface details. The inset radar images reveal billions of tons of polar water ice in shadowed craters. Above that, the mineralogy panel indicates rich reserves of organic compounds, silicates, and oxygen-rich minerals trapped in the rock. With gravity that preserves human bone density and ice that provides the basis for life support, Mercury possesses the fundamental chemical and physical requirements for long-term habitation. Terraforming Mercury requires a multi-generational strategy, focused first on neutralizing the solar wind and reducing the massive influx of heat. A colossal superconducting magnetic dipole at the L1 Lagrange point generates a protective magnetotail, deflecting incoming solar wind around the planet. With the wind deflected, a swarm of orbital mirrors is deployed, physically reducing the sunlight hitting the surface to Earth standard levels. By adjusting the angle of these mirrors, engineers can mechanically simulate a 24-hour diurnal cycle, giving humans a normal rhythm of day and night. Through a magnetic field and an adjustable sunshade, the Sun is downgraded from a deadly hazard into a highly controllable source of light and energy. The next step is atmospheric generation. Photolysis splits water molecules, turning polar ice into vapor, while electrolysis of surface silicates releases mass quantities of oxygen. To counteract the planet's severe nitrogen deficit, massive amounts of ammonia are transported from the outer solar system and released into the environment to act as a crucial buffer gas. A pressurized gas envelope allows for heat convection. As the atmosphere forms, heat redistributes from the day side to the night side, driving global hurricane-force superstorms across the cratered landscape. The orbital sunshades must be precisely angled to modulate local weather patterns and prevent these intense winds from damaging early surface settlements. Paraterraforming is an inherently violent physical process, requiring chaotic planetary engineering to force a dead rock to hold a breathable sky. Mercury completes 3 rotations for every 2 orbits around the Sun. This 3-to-2 spin-orbit resonance creates a 176 Earth-day solar cycle, where the Sun can appear to stop, move backward, and rise again in the sky. To survive the months-long stretches of intense day and freezing night, early colonies will rely on terminator cities. These massive enclosed habitats are mounted on giant ceramic tracks that circle the planet's equator. As the creeping dawn hits the track behind the city, the thermal expansion of the rails physically pushes the habitat forward, keeping it perpetually rolling through the twilight zone without additional power. For those seeking a stationary existence, ancient volcanic lava tubes, some large enough to house entire cities, offer absolute shielding from surface radiation and stable temperatures ranging between -25 and 17 degrees Celsius. Human survival on Mercury requires abandoning traditional stationary surface living in favor of either perpetual motion or deep subterranean settlement. As the atmosphere thickens, engineered extremophiles, specifically radiophiles and thermophiles, are deployed to break down the toxic regolith and bioleach metals, processing it into usable agricultural soil. Genetically tailored vascular plants, designed for high light and high gravity conditions, are then planted to establish a closed-loop biological shield that naturally recycles waste and regulates the environment. The final milestone of planetary engineering relies entirely on biology, designing life to manage an environment where it naturally shouldn't exist. The economic incentive driving this massive undertaking is energy. At perihelion, every square meter of Mercury's sun-facing surface receives up to 14 kilowatts of solar energy. Massive orbital arrays capture this immense, uninterrupted power and transmit it across the solar system using highly concentrated microwave and laser beams. Mercury's low escape velocity of just 4.25 kilometers per second allows electromagnetic mass drivers to effortlessly shoot refined iron, nickel, and silicon directly into space. These exported materials and the beamed solar energy formed the industrial foundation necessary to construct a Dyson swarm around the Sun. The transformation converts Mercury into the solar system's primary refinery and energy exporter, providing the fuel and metal needed to expand humanity's footprint toward the outer planets. Deciding to join that expansion means choosing between a life of perpetual motion on the Terminator or the stability of Earth.